Okay, good morning, everyone. Let's get started. We are approaching the end of the semester. We have a few lectures left. You're working on your third milestone. First of all, an apology. I didn't communicate properly to the TA. They might have removed quite a few points from your M1 or from your M2 if you didn't remind us about what your deliverables are. We're fixing that. We'll give the points back if we took some off. But remember, we can't keep track of all the 59 different final projects and where you all are in your baby steps towards those final project goals. So make sure every week when you submit your weekly milestone, you give us that bulleted list and let us know if you've made any changes along the way. Good? Okay. Back to lecture. So we are working our way through the seventh and final theme of the course. One of the things that makes evolutionary robotics different from all other branches of robotics research is we're attempting to try and optimize both the physical structure and the neural controller of the robot simultaneously. We've talked quite a bit in this course about how to do this using evolutionary algorithms, which are nice because they're algorithmically very simple. You can write an evolutionary algorithm in about a dozen lines of code, but it has this significant drawback, which is the trial and error nature. It's computationally inefficient. So last time, we started to look at some very recent work that's been conducted over the last few years that's figured out how to remove the evolutionary algorithm and replace it with gradient descent, which is a more complicated algorithm to implement. But it has a significant advantage, which is that it gets rid of the randomness, gets rid of the trial and error, and you can be guaranteed that on the next simulation, your robot is going to do a better job at what the robot did in the previous simulation. Sounds great, but there is still a limitation or Achilles heel for gradient descent, like there also is for evolutionary algorithms. What is it? What problem does gradient descent still suffer from? Haven't fixed everything.
Local optima.
Local optima, right? Still can get stuck in local optima. However, that being said, it's definitely much more computationally efficient. So let's return to it. We're going to return to our lecture on differentiable robots, which we'll finish up today, and then we'll start lecture 23 on. We'll start on lecture 3 on meta robots, robots within robots within robots within robots. Okay, back to differentiable robots. We ended last time by working our way through, partway through the backward pass. So we're going to continue talking about the forward and backward pass this morning. The forward pass is something that hopefully you're all familiar with at this point. The light is simulated. The light affects the values of the sensor neurons. The value of the sensor neurons via the synaptic weights affects the values of the motor neurons. The value of the motor neurons in turn affect omega, the turning speed of the wheel. The turning wheel of the wheel, the turning radius, the turning speed of the wheel at the next time step affects where the sensor is, which affects what the sensor value is, and around we go, right? Sense, think, act, sense, think, act, sense, think, act, until the end of the simulation. That's the end of the forward pass. Now, with gradient descent, we're going to, in effect, or the differentiable simulator, called Diff Tai Chi, different from the physics engine you've been using so far. That differentiable physics engine is designed so that it's now able to run the simulation in reverse, go backwards, and along the way determine for all of the parameters or all of the variables that make up your simulation, it's able to determine local gradients, meaning how you can change that parameter or value, like for example, omega, theta, the value of theta, the weight of the synapse, how the weight of that synapse should change, d theta, to change dl, loss or behavioral inefficiency. We know exactly, or the differentiable simulation knows exactly how to change that variable to change L. Specifically, how to change L for the better, to reduce L. Yeah? So far, so good? Loaded back into short-term memory? Okay. All right, so we ended last time by making our way partway through the backward pass. We had seen how it calculates the local gradient for turning radius, but that's the job of the physics engine. That's not something we want gradient descent to change. Theta is a different story. This is a value that at the beginning we chose randomly. We don't know what a good value for theta is. So we do want the differentiable simulator to compute dl over d theta. And then when we finish the backward pass, which we haven't finished yet, it's going to apply that local gradient. It's going to change theta a little bit, and it's going to guarantee for us that loss is going to come down. So far, so good. I want to make sure I don't lose anyone at this point.
Sorry, what was dw again?
This is d omega. This omega is the turning speed of the wheel. Okay. All right, so we've made it back to theta, and we now see how diff tai chi, this differentiable simulator, can alter the synaptic weights for the better, which is great. That's wonderful. But remember, in this course, we're also interested in trying to optimize not just the brain of the robot, which in this case is just 2 synapses. We also want to be able to optimize the body or the physical structure as well. So let's continue the backward pass. We can continue by going back to x. If you'll remember at the beginning of this lecture, I was flickering back and forth between 2 slides and showing the horizontal position of this sensor moving back and forth. Whoever built this simulation, not only did they randomly generate a value for theta, they also came up with a value for x. What is the horizontal position of these front sensors? They also had to make a whole bunch of other design decisions. What's the size of the wheel? What's the length and width of the main body of the robot? There's a whole bunch of other physical parameters that had to be set by the person who was setting up this simulator. The advance of this simulator and the big change in robotics over the last few years is now we can let gradient descent start to optimize the physical parameters of the robot as well, non-randomly. So in the same way that we use the chain rule, let me just go back for a moment. We use the chain rule to figure out, we first of all figured out this gradient. Then we use the chain rule to figure out this local gradient. We can keep going. We can keep applying the chain rule to figure out how to change x, dx, to change L, loss, dl. So in this backward pass, the physics engine knows how to alter x by a small amount. Remember, we're always making small changes because we have local gradients. The physics engine now knows how to alter x, the horizontal position of the sensor, so that L will also come down. Anybody see what it is? Should the sensor move to the left or right to ensure that the next time through this pass, the red arrow is going to be a little bit closer to the black arrow? We played this game before with theta, the synaptic weight. If the synaptic weight is stronger, does that make the robot turn more to the left or less to the left?
More to the left.
More to the left, right? So hold on to that intuition. What about x? If we move the sensor to the left, what happens? Is that going to increase L or decrease L?
It should decrease L a bit because it'll be closer to the light at the moment. So
Exactly. So let's think about moving x to the left first. If we move x to the left, as you say, the sensor is going to be closer to the light, which means more light is falling on that sensor, which means the signal getting down to the wheel is stronger, which means the wheel spins faster, which means the robot turns more to the left, which means the red arrow tilts a little bit more to the left, and we've reduced L. So in this very, very, very simple example, this is why Bradenburg vehicles are so great, you can actually do it with human intuition. You can actually figure out For this moment in time, under these circumstances, you can actually figure out what the local gradients should be. We know that omega should turn faster, or if omega turns faster, that reduces L. If theta is bigger, that also reduces L. And if x is further to the left, the sensor is further to the left, that also brings down L. We're able to, in our heads, figure out all these local gradients. Luckily, that's what the differentiable simulator does for us. You can imagine where all this is going. The minute the robot gets more complicated and we have a more complicated fitness function, forget about it. You can't figure out these local gradients. Okay, so let's draw a little bit here. What have we done? We've started from L, and on the backward pass, we've gone to omega. We know the gradient there, but we don't apply it, because that's something the physics engine calculates on its own. We've gone back, omega, we've gone back to theta, the synaptic weight. That's something we had to guess at random. So yes, we're going to tell the physics engine, we're going to tell gradient descent to apply the local gradient there. And we've also gone back to x, the horizontal position of the left sensor. That's something we also had to kind of decide relatively arbitrarily when we set up the simulation. So maybe we didn't pick a good x. So we're going to tell gradient descent to also apply the local gradient that it calculates here. But we've only followed this path back. So I'm going to now put, I apologize for the bad notation here. I'm going to use another L. I'm going to put a subscript L here, which is for the things on the left. Actually, sorry, let's make this more complicated. We looked at the rotational velocity of the right wheel in our example so far. We've looked at this particular theta. I'll put it on the left-hand side because it connects to the left sensor. And we've talked about the horizontal position of the left sensor. What about theta? What about omega over here? We also have to think about this omega, the speed of this wheel. We have to think about this theta, the strength of this synapse, and we also have to think about x, the horizontal position of this sensor as well. So let's add that backward chain. From L, from loss, the differentiable simulator also is able to calculate the local gradient for the turning speed of the left wheel. Keep going back. It will also know the local gradient of this synaptic weight that connects to the right sensor, and backward to x sub r, the horizontal position of the right sensor. We can keep going back. So what have we drawn here? We've drawn here basically the way in which gradient descent applies blame. Who did the wrong thing, and how should we change that thing in order to make things better? This is known as a computational graph. When you apply gradient descent to a traditional neural network, where you have a whole bunch of synaptic weights, you also have a computational graph. Luckily, you never see this computational graph. It's hidden from you. It's taken care of by gradient descent. So far, so good? Okay. I've oversimplified things for our purposes here. One of the simplifications I now want to roll back, which is time. We haven't talked about time. In our cartoon example here, we've only been talking about the state of the robot and local gradients for this moment in time in the simulator. So let's add another subscript t, to all of our variables here. What does this subscript mean? What it means, omega sub rt means the turning speed of the right wheel at that moment in time. Let's go back here. So think about this. When we have our turning speed of the wheel at time t, that's going to affect x sub L sub t. It's going to affect where the sensor is at the next time step. Remember, sense, think, act, sense, think, act, sense, think, act. So I'm going to keep going backwards here. I should have written this lower. The position of this sensor is also a function of the speed of the wheel at the previous time step, t minus 1, and same thing over here, t minus 1. So this computational graph, remember, we're working backwards through the simulator. What do I mean by backwards? We start with loss. We go to the speed of the wheels, which was what affected this trajectory. Back, we're doing, instead of sense, think, act, we're doing act, think, sense at the very last time step of the simulation. Then we go backwards again. Actually, let me draw this. Let me try and draw this more simply. Sense, think, act, which affects, there's a sensor repercussion for that action. So this is sense, think, act at the tth time step. This action has a sensory repercussion at the next time step. The robot thinks again and acts again, and so on. So we're flowing forward in time. Sense, think, act. Actions have sensory repercussions at the next time step. Sense, think, act. Sense, think, act. Sense, think, act. When we go backwards, we're actually going backwards from actions to thinking to sensing. The sensing is coming from the sensors up here. When we go in reverse, we're going to go action, think, sense, action, think, sense. Everybody following that so far? Have I lost folks? Okay, so this computational graph that I've just written, I've also left out a few variables. So the horizontal position of the sensor affects the sensor value, which affects, multiplied by theta, affects the turning radius of the wheel, and so on. So this computational graph is actually huge. If we run this simulation for 1,000 time steps, there are 1,000 of these going up and up and up and up. So when I tell you that the differentiable simulator is able to calculate and then in some cases apply the local gradients, it's actually computing the local gradient, and it's able to tell us how to change this theta at this time to reduce L. It also tells us how to change the same theta at the previous time step. There's 1,000 instances of this variable in the computational graph. Everybody see that? So what do we do with theta sub L? How do we actually change theta sub L once we've got all the way back through the computational graph? Ideas?
Do you want to take all the suggested changes for thetas at different time steps and average them to get an average change?
Exactly. So let's put our loss landscape back up on the board for our intuition. Let's just deal with one variable at a time. I'm arbitrarily choosing the left, one of the two synaptic weights. We have L on the vertical axis here, and remember, in gradient descent, we're trying to minimize L. We're trying to minimize loss. We're at a particular point. We don't have a population anymore. In the evolutionary algorithm, we had a population. In gradient descent, we have just one set of synaptic weights, the x values, and so on. And for example, let's imagine that gradient descent tells us that the local gradient of this variable at time t looks like this. The local gradient at another point in time was this for the same variable. We have 1,000 of these local gradients. We're going to take the average of all of these gradients, Apologies for my poor drawing skills here. We're going to take the average of all these 1,000 local gradients, that gradient descent calculated going back through the computational graph, and that tells us how to change theta so that L will come down. So in my little cartoon example here on the board, we're going to reduce theta sub L when we get all the way back through the computational graph. Question?
I thought with this, you go all the way to the end, to the very first time step to change it, and you take that value, not the average of them. Is that just incorrect?
It's possible you could take the one at the beginning if you want, but there's different ways to do it. So it depends on the condition. Sometimes it works, sometimes it doesn't. Generally speaking, you want to take the average, which is giving you more information. Okay. All right, let's again now try and simplify again. Let's continue this example. Let's imagine we've gotten all the way back through this computational graph, all the way back to T0, the beginning of simulation. We take this averaged local gradient, we use it to figure out how to change theta sub L, and we make that small change to theta sub L. Remember that some of the other variables like x, which are things that we could change, we could also apply those gradients. For now, let's assume we just choose not to do so. We only apply this one. And now we run the simulation forward again for a second time. We're going very slowly here, right? There aren't thousands of robots being run in thousands of simulations. We're talking about just one simulation at a time, and one robot with a set of x's, a set of thetas. We're now going to do the forward pass again for the second time. What's going to happen now? We've made one change. We've altered theta sub L by a small amount. This is what we've been building up to in this lecture.
You're now going to, at that new point, you're going to get all the same averages and then basically do it again.
You're talking about the second backward pass.
Yeah.
We haven't got there yet. What happens at the end of this second forward pass? We've run the simulation forward a second time. What have we been expending all this intellectual blood, sweat, and tears for? This is the magic moment. It gets better. Loss is guaranteed to go down. It might go down by a very, very small amount, depending how much we've made a change here, but we have a guarantee, thank gosh. Finally in this class, we have a guarantee. Evolutionary algorithms, I love them, but there's no guarantees, right? Most of the time you make a small change and things get worse, as you probably now have a lot of experience with. Okay, great. We made a small change. As was mentioned, we now do a second backward pass. We're going to get a whole bunch of new local gradients at our new position, and off we go. In practice, you're usually not just applying the gradient to one variable. We might apply it to both thetas, both x's. We might also accumulate the local gradients for the length and width of the box that makes up the robot and the sizes of the wheels. And at the end of the backward pass, we make a slight tweak to all of those variables. And as long as those tweaks are small enough, we're guaranteed for the robot to reduce loss. Okay. All right, thank you for your patience. We've spent a lot of time doing this with the Bratenberg vehicle. Let's now see a more interesting case. Together with some of my collaborators and students, we published a paper 3 years ago now reporting this application, but not to Bratenberg vehicles, to a more complicated robot. And I'm going to walk you through step by step a figure from this paper. We're going to start with this scatter plot up here in the upper left, which is a little bit odd because it's got people's names attached to it. Whenever we look at any graph, we always start by making sure we understand the horizontal axis, then the vertical axis. So the horizontal axis is year of publication. You can probably guess from that that the points are going to represent papers. These are papers published in the literature. And the vertical axis here is design attempts. What is a design attempt? One forward pass. Basically, you can think of a design attempt as a simulation. For most of the literature, for the last 25 years or so, as you've seen in this class, the number of design attempts is somewhere between 10,000, 100,000, 10,000 or 100,000. These points all up here, these are all evolutionary robotics experiments. In those papers, the authors reported we ran an evolutionary algorithm on a simulated robot, and we got this cool simulated robot after about 10 to the 4 or 10 to the 5 simulations. So all of these papers that are reported here are evolutionary robotics papers. There are many more evolutionary robotics papers than these. This is a subset of evolutionary robotics papers that were chosen because at the end, when the authors had a cool simulated robot, they built it. So for every one of these points, there was an attempt to cross the sim to real gap. So what is this plot telling us? It's telling us that for the last 25 years, people have been evolving robots in simulation and then transferring them to reality, and they've spent quite a bit of computational effort before trying to cross the gap. Okay, there's a couple of exceptions here, outliers. Let's look at this one here, Broadbeck et al. This group of researchers threw away the simulator altogether. They made something that was kind of like a 3D printer that could make physical robots, and they made about 100 of them. So these folks decided to do away with the sim to real gap altogether by throwing away sim. Okay, not bad, but they still had to build 100 physical robots that had different bodies and brains. I know these authors very well. It was a huge, long, painful process. Possibly as 3D printers get better and it gets easier and easier to print large numbers of physical machines, maybe this approach will be the one that eventually wins. Maybe this is the path towards autonomous, safe, and useful machines. Just get rid of sim altogether. We'll see. The paper that we're going to talk about now from 2023, these folks, myself included, these authors, ran 10 simulations, 10 to the 1, before attempting to cross the sim to real gap. Sounds crazy. How can we try and cross the sim to real gap with only 10 simulations? It's because we're going to see gradient descent in action. All these other papers used an evolutionary algorithm. We used gradient descent. Okay. What does this robot look like? Kind of looks like it's in camouflage here. It's a very odd-looking physical robot. It's covered in cornstarch, and the ground is covered in cornstarch as well. Why? So it's a messy experiment also. What's with the cornstarch? Friction. The robot you're going to see here is made out of silicone rubber, the soft rubber that we saw the soft robots made out of in a moment. You put cornstarch on silicone rubber and cornstarch on the tabletop that the robot's moving over, and you get very high friction, which is what we want to get this robot to move to the right. Okay. The little green squiggle that you see under here, this is reporting the robot moving and how far it moved to the right, which was about, there's 2 centimeters, 4 centimeters, 6 centimeters, so about this far to the right. It's a pretty small robot, didn't move very far, but we optimized it in simulation using just 10 simulations and managed to cross the sim to real gap. I'm going to do a lot of patting of my own back in this lecture today. All right, you see there's a tube leaving the top of the robot. This should now be a pretty strong hint to how this robot is actuated, how it's moving. What do you think? Where have we seen this before?
The like air pressure cells.
So this robot, as you're going to see, is similar to the voxel-based robots we saw before. Not quite, but it's also partially hollow. And we're going to push pressurized air in and pull pressurized air out. Every time we do, there's going to be one of these little green arcs. It's going to take a step, pull, push, air, step, pull, push, step, pull, push, step, and it's going to move to the right. Okay, let's go back to sim. So I've jumped ahead just to show you what real looks like. Let's start with sim, and we're going to start with the first forward pass. What is this robot? How did we actually define the physical structure of this robot? In the previous example, when we were looking at Bratenberg vehicles, there's not many physical parameters to optimize. There's the positions of the sensors, the shape of the box, the size of the wheels. That's about it. One of the fun things about gradient descent is because it's so computationally efficient, we can twiddle with many more parameters at once. This is also why we're all currently enjoying an AI high summer, is gradient descent allows you to simultaneously tune, or allows Google and OpenAI to simultaneously improve billions of synaptic weights at once. In the robot you're going to see here, the gradient descent is simultaneously going to optimize hundreds of physical parameters at once. What are those physical parameters? We started by assuming the robot is made up of a chunk of silicone, like you see here, and we then randomly punch a whole bunch of holes through this block of silicone. So we basically turn this block into a block of Swiss cheese. The holes are shown in white here, and they're punched all the way through. So we've got this Swiss cheese, and we're initially choosing these holes at random. You can see they're randomly distributed across the body of the robot. So what does that look like in reality? It's very difficult to see here. It's very difficult to see the small holes. There are a few of them in here. They pass all the way through the body to the other side. So this allows us, or allows gradient descent, to play with a robot with a complex geometry. Everybody see this in their heads so far? Okay. You'll see there are also some larger red circles. The larger red circles are hollow spherical cavities inside the body of the robot. You can think of these red holes as like your lungs. They're hollow cavities inside the body of the robot. When we pass air into the top of the robot, in this robot, for example, the air would go all the way into this complex internal cavity, but not into the rest of these hollow cavities, because they're not connected to the one that connects to the top center. So far, so good? Okay. If you apply air into and out of this robot, it sort of deforms in place. It doesn't move to the right at all. That's the forward pass. And I'm going to show you these simulations in a moment, but we're going to keep things at a high level for now. So in simulation, we increase the air pressure inside this hollow internal cavity, which deforms the shape of the robot, but it doesn't really move anywhere. So L, I still got L on the board, L is high. We want the robot to move to the right, but it stayed where it is. So the horizontal position of the robot and some horizontal position way out to the right, that distance is large. L is large. We've finished the forward pass. What do you think happens on the backward pass? Sorry, one last detail I forgot to mention. I've talked you through the body of the robot. What's the brain of the robot? The brain of the robot is a central pattern generator. It's just a single sinusoidal pattern which controls the rate at which we put air in and the rate at which we pull air out. Air in, air out, air in, air out at a constant sinusoidal pattern. What do you think happens on the backward pass? We're going to collect tens of thousands, possibly millions of local gradients in this computational graph. Who's on this computational graph?
Is it the locations of those red circles, the holes that are punched, and then the different features of the sinusoidal wave?
Bingo. So the horizontal and vertical positions of every white circle that you see here, every hole that's punched through the robot, and the horizontal and vertical position of every single red circle that you see here. And along the way, gradient descent also computes the local gradients for how the sine wave of the CPG should be different to reduce loss, to make the robot move further to the right. We were feeling cocky when we did this experiment, and we just threw away the local gradients for the sine wave. So what you're going to see in this experiment is we're only going to allow the gradient descent to optimize the body. We're going to keep the CPG as is. So in essence, gradient descent is optimizing or looking for a good body that travels to the right when it gets this pattern of pressurized air in, pressurized air out. Everybody see that? Okay.
Like the body is 3D, but the image is 2D. So
The robot is 3D, kind of. We, again, tried to keep this simple. So when we did this experiment 3 years ago, this differentiable simulator we've been talking about, Diff Tai Chi, was brand new. And as you can imagine, version 0.0001 of any software, little flaky. So we tried to keep things simple, and we ran a 2D simulation. As we started running it, we started to scratch our heads and thought, well, we do want to try and cross the gap. How are we going to make a perfectly 2D robot? We can't. We just extend it out in the 3D plane. So yes, of course, any physical robot is going to be three-dimensional, but it's really two-dimensional. Question?
Do the holes just allow like controlled air escape, or why were the holes added?
So the holes were added to allow gradient descent to play with the shape of the robot, which doesn't look like much at the moment. This is the final optimized structure, and it may be difficult to see, but this robot has some stubby legs here. So I'm kind of giving away the punchline. You can see in the real robot where gradient descent is going to take us, but I'm going to show you in a moment how it got us there. So we added the holes so gradient descent could play with shape. And we added the red, the internal cavities, to allow it to play with where actuation goes in the body. Where does the pressurized air go? And when the pressurized air leaves those areas, how does it pull those parts of the body together? You don't really deform when you take a breath in and a breath out, but you would if we put enough pressurized air and we pulled enough pressurized air out. That's what's going to happen with our little robot here. So far, so good? Okay, let's go. So this snapshot is after one forward pass. So we have a randomly built body, and we have loss down here, 0.02 body lengths per second. So this is a body length, and you can see the little green stitching. So this robot actually did move to the right. It moved to the right by this amount. It kind of deforms like this, leans a little bit to the right. Okay. Now we allow gradient descent to run the simulation in reverse, computes all the local gradients, and applies them to every white circle and every red circle, which gives this shape. I'll give you 10, 15 seconds to look at it. You can kind of see where the white circles went and where the red circles went. Remember, when we apply local gradients, we try and only make a small move for that parameter. Okay, so we got a little bit of change. We've just run the backward pass. Now we run the forward pass for a second time. So we simulate this robot. This is the second simulation we've run. And now it moves 0.09 body lengths per second to the right. and it travels a little bit further to the right. Might be difficult to see in the back of the room, but you can see that this green trajectory is jinking up and down. You can see the results of the oscillating pressurized air in and out. When we got this result, we got very excited. We were dealing with a very shaky early version of a differentiable simulator connected to gradient descent. We were dealing with a robot that's much more complicated than a Bratenberg vehicle, and everything's working. We got what we want, which is non-random improvement. So far, so good. Questions, comments? Have I lost anyone? Okay. Third forward pass. Fourth forward pass. Fifth forward pass. What's happening? We've only run 5 simulations so far. What's happening? Where's the air going? It's not going far. It's still, the air is going in here and into this cavity. So this blob of red up here is getting smaller and bigger as air is pulled out and pushed back in. What do you think's happening? Can you run a simulation of this flexible soft robot in your head?
I'm imagining as you pull air out, it kind of like lifts the front up a little bit, and then as you push air in, it kind of expands that side and pushes it.
It lifts the front up. The front what? Legs. So we got really excited when we got to this point because this is something we weren't expecting. This is, well, I don't know that we were expecting it. We were hoping for this. This is sort of the debugging sanity check part. Everything's working. This was a surprise. Absolutely. When we pulled air out of this chamber got smaller and pulled this front part up, and this little dangling part at the front came up and forward. Remember our lecture about legged locomotion. This is starting to look familiar. 6th simulation, 7th simulation, 8th, 9th, 10th. What happened?
It plateaued a bit, but still making like it's still going.
It's plateaued a little bit. We jumped from 0.46 to 0.48. We now not only have a front leg, but a middle and back leg. So again, I'll play the video for you in a moment, but you can kind of guess what's going to happen. Tell me about the red parts. What's going on now?
They're still not all connected, but the one that's taking air is expanded all the way down to the bottom.
Absolutely. The pressurized air is reaching all the way down here to the sole of the foot of this back, quote unquote, leg. You'll notice that there are cavities forming, hollow cavities forming on the anterior part of each quote unquote leg. Anterior means on the front, posterior on the back. We went back to the beginning and we did this all again. We set all of the positions of the white circles and the red circles randomly and ran things forward again for another 10 simulations and got more or less the same pattern. Sometimes we got 2 legs, sometimes we got 4 legs, but they were always they always had this diagonal shape, and cavities always formed on the anterior side of each leg. Kind of interesting. Possibly a local optimum. Remember, gradient descent doesn't inoculate us against getting trapped in local optimum, but it's pretty good. This thing moves half a body length per second. We'll take it. Okay. Any questions before we see this creature in action? Okay. This is just another visualization. We were playing back all 10 of these robots, one on top of each other. Sorry, not on top of each other. This is a time-lapse video of attempt or robot 1. Doesn't go anywhere. Here's a time-lapse of robot 3. You can see it sort of moving. And then here's the 10th robot moving. You can see it's a little hard to see because of all the shapes that are overlaid. The robot isn't deforming much. It's kind of shuffling and sort of shuffling its legs along. So not definitely statically stable, dynamically stable. This robot's not doing anything crazy, but it's actually developing a regular gait. Okay. Why am I missing the video for this? It's the best part. There it is. Okay. All right, you're going to watch this video run, and you're going to see a timer running in the middle here. This is us showing off again. Those 10 simulations, they took about 30 seconds to run on a laptop, right? We're not simulating millions of robots anymore. So it's so computationally efficient, things are going to happen in terms of seconds of what's called wall clock time, right? We're literally just watching the clock, and this is how long the optimization process actually took. Here we go. All right, there's our original random robot. Here's after the first forward pass. 3 seconds of elapsed so far. You're going to do one backward pass. Here it goes. There goes the backward pass. Second forward pass. 10 seconds have elapsed. Second backward pass. Third forward pass. In the backward pass, you're actually seeing the gradients being applied. Third backward pass. Fourth forward pass. All right, fifth, sixth, seventh, eighth, ninth. You're watching all the backward passes. And after 27 seconds, 29 seconds, 30 seconds, 10th forward pass. And then there's the jump to real with a lot of cornstarch to increase friction. Okay. All right, in the second minute of this video, this is just some of the engineering details. I'm going to skip over some of this. This is some technical details of the backward pass. It's too detailed for our purposes. All right, we're just trying to visually depict what the backward pass is doing. Okay, I think actually in the interest of time, we'll skip over this. Okay. All right, where were we? Okay, any questions about that? Yes?
How difficult was it to actually make this robot? I mean, this seems like a fairly complicated architecture to make into an actual robot.
Good question. Okay, so remember inside the physical robot, there are some hollow cavities, and there are also some holes that are punched all the way through. Seems like kind of a weird, arbitrary way to do things. Part of the reason why we did this is because we wanted to see gradient descent co-optimize many physical parameters at once. The other reason is that our collaborators on this research project at MIT, they had a device, they had a way to manufacture robots kind of this shape. So let me describe how this works. You all know about a waffle maker, right? It's got a particular shape. You pour the batter in, and then you close it up. It's like a clamshell. So the device I'm about to explain is very much like a waffle maker. Imagine the bottom half of this waffle maker is a piece of metal that is exactly this shape. You pour into that metal mold, you pour in a liquid. It's not waffle batter. You've seen it already actually in this class.
Silicone.
Silicone, which kind of silicone? There's the kind that's liquid at room temperature.
The dragon skin?
Dragon skin. So it's a particular type of silicone rubber that's liquid at room temperature. We pour that in, and the liquid spills out and forms and fills all the gray parts. So in the mold, imagine there are cylinders poking up from the bottom of the mold. They're pointing upwards, and they obviously, that cylinder resists the dragon skin. The dragon skin flows around that cylinder. Same thing actually for the red circles. And you get basically this gray shape with an enclosed boundary. So far, so good. You can probably guess where this is going. The upper half of the waffle maker is the reflected shape. It's exactly the same shape, but flipped along the y-axis, flipped along the long top half of the robot. So if our robot looks something like this, the top half looks something like, let's see if I can draw this, like that. Pour the liquid dragon skin into this, close it up, put it in the oven, heat it up. Dragon skin, when you bake it, solidifies. The two halves connect. Take it out of the oven, open it up, wait for it to cool, and when you pull it out, what do you get out? You get this thing. I should add some slides about this. Can everybody see this in their heads? That's how we built it. Question?
How quickly could you do that?
What did it take? A couple hours. I mean, it took weeks to figure out how to make the waffle maker and the molds and all the rest. But when we went to actually print this thing, not too long, not bad. Okay, you can guess that many attempts did not cross the reality gap. Respect to the reality gap, it's hard to cross. But there were a few designs that actually did cross the gap. Okay, all right. Showing off a little bit more. Now that we can evolve the physical structure of a robot so fast, just 10 simulations, not only are we reducing the time and the computational effort, we no longer need to run this on a supercomputer. Actually, we don't even need to run it anymore on a laptop. You can do it on your phone. So get out your phone and point it to this URL. Sorry if it's so small. I keep meaning to make a QR code. I haven't got around to that yet. So direct the browser on your phone to that URL, which is bit.ly as always, good old bit.ly. Uppercase E, Z, 3A. Lowercase k. It should take you to a Google Colab, which is the way to run some code in the cloud. Is everyone getting to Google Colab? Yeah? Okay. All right. When you do, tap the three horizontal bars at the top left. It'll drop down a drop-down menu. You should see in that drop-down menu Runtime. When you tap Runtime, a sub-menu should open up, and you should see the option Run All. Tap Run All. Hands up if you got that far. Good, okay. All right, so this URL, 3 bars, tap Runtime, tap Run All. When you tap Run All, it's going to start running that code on one of Google's data centers for you. Thank you, Google. Okay. It's not going to be too much of a computational lift for Google because your code is about to do about 20 simulations over about 60 seconds. At the end of 60 seconds, your phone is going to download a video into your gallery, which is a before and after snapshot of you running gradient descent on Google's cloud. Here's the example that I got. Here's a random soft robot, Very different from the robot we just saw. We're back to a mass spring model. I think we've seen some robots that look like this before. What a surprise. The loss function, as always, is moved to the right. Here's the randomly created robot that my code generated, and after 60 seconds, I got back this robot. Anyone received a video in their gallery? Yes? Okay. Yours will probably look quite different from this one, but hopefully the robot in the bottom half of the video moves further to the right than the one on the left. So there's about 20 of you in the room right now. We just ran 20 instances of gradient descent in about a minute. Not bad. Okay. Any questions about that before we move on?